Hello and welcome to the first video of Chapter 15. I'll give you an introduction into NMR spectroscopy. We're going to focus on three main areas in this video: the what, why, and how of NMR spectroscopy. And then we'll talk about terms that we use to describe the chemical shift, that's the position of a signal in an NMR spectrum. And then we'll look at important features in a proton NMR spectrum. So let's get started. So let's start off with what this is an acronym here, what the N, M, and R stand for in NMR spectroscopies. Spectroscopy, you know, is the study of how light interacts with matter. Okay, so we're using radio frequency. So I'm going to say radio frequency. Light or electromagnetic energy is the type of light that we're using here. The N stands for nuclear. So it must be something involving the nucleus involved. In order for a substance to be, active towards NMR spectroscopy, inside of the nucleus of one or more of the atoms in the compound you're trying to probe, there needs to be an odd number of protons and or an odd number of neutrons. And when that happens, there's a quantum mechanical property called nuclear spin that substance has. So proton NMR, H1 is the most abundant isotope of hydrogen, and this is one way I can depict it. It has one proton and no neutrons, so it has nuclear spin since it has an odd number of protons. Now, the most abundant isotope of carbon is carbon-12, and that does not have an odd number of protons and or neutrons. However, there's another isotope, less abundant one, carbon-13, that does then have nuclear spin thanks to the odd number of neutrons there, right? Okay, so that's the nuclear piece. The next piece here, M, is for magnetic. So in NMR spectroscopy, you need a magnet to generate a magnetic field. And we'll talk about why that's the case and how that relates to nuclear spin. Okay? And then the R stands for resonance. This is not referring to the type of resonance that you are used to, like drawing resonance structures for benzene or for a carboxylate anion. Okay, so we'll talk about how what this is referring to. Okay, so now we know these words and something about what they mean. Let's talk about why we use NMR spectroscopy in organic chemistry. So this is the most powerful tool that we have in our toolkit for structure determination. Now, you're already familiar maybe with some other types of spectroscopies that are useful for helping us along the path to getting to determine the structure of a compound. You've learned about mass spectrometry, which you can figure out the molecular size and formula of the compound. And then you've talked about infrared spectrometry, which is really useful for identifying functional groups. Okay, but for proton NMR spectroscopy, that's going to determine the number and types of hydrogens in a compound, and carbon-13 NMR spectroscopy is going to determine the number and type of carbons in a compound. So we can determine the carbon-hydrogen framework of our compound using this type of spectroscopy. So it's really, really, really powerful, okay? So typically in a laboratory setting, you carry out some type of synthesis, you purify the compound as best you can, and then you go take an NMR to see, did you get what you think you got? All right, so let's talk, before we get to these other two, I'm going to spend most of this video talking about number one. Let's talk a little bit about how it works. So I mentioned that you need an odd number of protons and or neutrons in order for you to probe it, for this type of spectroscopy to work. And that's because when you have an odd number of protons and or neutrons, you have that nuclear spin. I'm just going to write down nuclear spin. Okay. So let's take a look at how this works. So let's imagine that we have a charged particle, a proton. This will be very analogous to what you saw in general chemistry with an electron spinning on its axis, but now we're going to take a proton. And so a proton is a charged particle, right? I'm just going to go ahead. Here's our little proton. And let's imagine here that it is spinning on its axis. And when it does that, it creates, or it's spinning. And if it's spinning, here's our axis. Spinning on its axis, it's going to create a magnetic field. Okay, so we can treat this tiny proton like it's a little bar magnet. Okay, so let's say instead of just having one proton, let's get a bunch of protons. So I'm going to use, instead of drawing the circle and showing it spinning and drawing the little magnetic moment, I'm just going to use the arrow to indicate the proton. So if we don't have a magnetic field present and we have a bunch of protons and we were able to somehow take snapshots of what their little bar magnets are like, we would see that they're in all different directions. So they're randomly oriented. Okay, I'm trying to make this look random. Hopefully I'm doing okay at it. There, okay. So if there's no magnetic field present, you're gonna have here, we've got a collection of protons and they're all randomly oriented. Now, if we apply a magnetic field, so I'm going to go ahead and here's my magnetic field, B0. Okay, so there's my magnetic field that I'm going to apply. What is going to happen is that the nuclei, each nucleus can orient in one of two ways. It can either orient itself with or parallel with that external magnetic field, so this would be with or parallel to it, or it can be oriented against or anti-parallel to that external magnetic field. And what we find is that most of the nuclei, not all, but most, will orient with the magnetic field or parallel, but some will be oriented against or anti-parallel. So there are two energy states possible for the nucleus when we apply a magnetic field. Okay. And one is lower in energy. That's the one that is going with or parallel to the magnetic field. And the other one that's slightly higher in energy is if it's against or anti-parallel that magnetic field. So we see more nuclei in a magnetic field that are lined up with or parallel to that external magnetic field than against it, because that first state is lower in energy. Okay. So here I've got my external magnetic field, and I've got these two possible energy states for the nucleus: parallel or with the magnetic field, and anti-parallel, or against the magnetic field. Okay, so since this is the most common energy state, with or parallel, I've gone ahead and put that in here. All right, so this is why the word nuclear is in NMR, because we're talking about nuclear spin states. Okay, so and then the word magnet, because we've applied an external magnetic field. Okay. And now, since it's spectroscopy, we know we need light. So I've abbreviated the light with h nu, since the energy of the light is equal to h nu. So nu is that funny looking V. Remember, that's the abbreviation for frequency, the frequency of the light. And we're going to be using radio frequency for this. So this is very low energy light. Okay. All right. So now this difference in energy between these two states, remember this one was parallel or with the magnetic field, and this one is anti-parallel or against the magnetic field. This difference in energy is very small. Okay. And it depends on the strength of the external magnetic field. So the stronger this external magnetic field is, the bigger the delta E is. Okay. All right. So if we use, so what we're going to do, we're going to shine some radio frequency light. Okay. And this will be our external energy source. When it matches this energy difference, delta E, between these two states, the energy is absorbed and it causes the nucleus to do what's called a spin flip. Okay? And it goes from being parallel to anti-parallel, or against that applied magnetic field. Okay? So this difference in energy, again, corresponds with energy in the radio frequency part of the electromagnetic spectrum. And so a big take-home message that you need to understand here is that NMR spectroscopy is super safe. Okay. Now, when the nucleus falls back to the lower energy state, there's a detector that measures that energy that's released, and that will correspond to this energy difference. And you get a little blip on the spectrum, and that's your signal or your absorption. So when this occurs, we say that the nucleus is in resonance. Okay, and that's where the term resonance comes from, and why we call it NMR spectroscopy. Okay. All right. So hopefully that's helpful for giving you some background about that. Now, if all of the protons in a compound absorbed at the same frequency in a given external magnetic field, then the spectra of all compounds would consist of a single signal, and that would be super sad. Lucky for us, that's not the case. So protons in different environments absorb at different frequencies. So that they're distinguishable then by proton NMR spectroscopy. Okay. All right. So let's go ahead and take a look at what an NMR spectrum looks like. So an NMR spectrum is going to plot intensity on the y-axis, increasing in this direction, against the chemical shift on the x-axis, but the direction here goes, it increases from right to left. So this is our chemical shift. And it's, if you see this delta, this is a delta symbol here, Greek letter, that is the abbreviation for chemical shift. So delta just means chemical shift. And this is measured in parts per million. And in a proton NMR spectrum, I'm gonna, oh, hold on just a second. Okay, sorry. So we're talking about the chemical shift on the x-axis is increasing from right to left. For proton NMR, you're gonna see this go from 0 up to anywhere from 10 to 12 ppm, and that stands for parts per million. Going from right to left is also increasing in the frequency. Okay, and so this, remember, frequency is abbreviated with that nu. Okay, so usually at 0, when you take your NMR spectrum, so imagine in the lab, you've isolated your compound, you synthesized it, purified it, right? Usually end up with some kind of solid, let's say, and you want to take the NMR spectrum of the compound. You're going to have to take it and put it in a solution. It needs to be in a liquid state. So you're going to take it and you're going to dissolve it in a deuterated solvent. Deuterated has to be a deuterated solvent, meaning you have H2 instead of H1. Usually we'll use something like, I don't know, deuterated chloroform. So that's CdCl3. Okay, so remember, this is the same thing as deuterium. And so you use a deuterated solvent to dissolve your compound so that you don't have protons from the solvent overlapping with protons in the compound you're taking the NMR of, that you're interested in. And as part of that solvent, you usually have, when you buy deuterated solvents, they usually come with TMS already in it. TMS is tetramethylsilane, and we use it to set the 0, okay? So you're gonna see at 0 a TMS signal. And then we're going to see signals here. Let's say I'm going to do here in a minute an example of, let's make this a really big signal here, around 1, 2, 3. Let's do then a smaller one here, 3. So here, and this keeps going all the way up, I've got 2 signals appearing, and one is to the right. So if a signal is to the right in terms of the chemical shift, we say that it is up field and shielded. We'll learn why it's called that. So signals that are to the right in an NMR spectrum are upfield or shielded. And we're going to see that they have, so going in this direction, they have increasing electron density around the nucleus. And signals that are to the left on the NMR spectrum are referred to as being down field. Also, they can be described as being de-shielded. Okay, and that's because they have decreased electron density around their nucleus. So these terms here, upfield, downfield, shielded, and de-shielded, are super, super important. We're going to use them and see them a great deal for describing the chemical shifts of signals in both proton and carbon NMR. So here we have two signals appearing. This one is the most upfield or shielded. This one is farther downfield, so it's more deshielded. So in an NMR spectrum, signals to the right are described this way, signals to the left are described this way. Okay, so where a proton absorbs depends on its electronic environment or its chemical environment. Protons that have increased electron density around their nucleus end up being what we call shielded from the external magnetic field that's applied, okay? Because these electrons, these are also spinning on their axis and creating a magnetic field that can oppose the external magnetic field. And so you end up, their delta E is smaller, so they resonate at a lower frequency, okay, than those that are deshielded. How do you make a proton deshielded? So proton is attached to a carbon, and if that carbon is attached to something really electronegative, that is going to withdraw electron density from the proton, deshielding it, so that the signal then, when it resonates, that absorption will be farther downfield. Okay. All right. So in your textbook, you'll notice that you are given this formula, and you may use it in lab. I don't know if they still do that anymore, but this is not something you need to learn for this class. So this delta, the chemical shift, we need, as scientists, we want to be able to report this in a way that is independent of the NMR spectrometer that we're using, independent of how big the magnet is that we have. So to do that, we have to report the chemical shift in ppm. And so where that comes from is we can get that chemical shift by taking that observed shift from tetramethylsilane in hertz. Let's see if I can get this in here. So in hertz, remember that's a unit of frequency, divided by the operating frequency of the instrument in hertz. And so this way, the chemical shift doesn't depend on the individual spectrometer, okay? So I only mention this so that you have some understanding of why the chemical shift on one spectrometer should be the same as the chemical shift on a different spectrometer, even though they are different, have different sized magnets, let's say. Okay. All right. So let's go ahead, and I'm going to continue to use this example here. This happens to be what I've drawn out is the proton NMR spectrum for something called MTBE. Okay, this stands for methyl tert-butyl ether. And I've just written it out this way so we can break apart the name. Okay. So ether is something that I think you ended up talking about towards the end of 301. So the ether, remember we have an oxygen that's going to be sandwiched between two carbons. On one side, the alkyl group is a methyl group, CH3. On the other side, it's a tert-butyl group. Okay, so I'll go ahead and draw that. Okay, so the NMR spectrum of this compound, we have just two proton signals. And that means that there are just two proton environments. So let's identify those environments, and let's try to figure out which proton signal belongs to which protons in the structure of the compound. Okay, so as a side note here, methyl tert-butyl ether was used in the US for a while as a gasoline additive. It's been banned. It's still used in some other countries, but it was used to reduce engine knock. Okay, so we've got these 3 protons here. They're all in the same electronic and chemical environment as each other, all 3 of these, right? All 3 of them are attached to the same carbon, and that carbon is attached to this oxygen. So these represent protons in one type of environment, and they're going to produce a signal. Okay. These methyl groups, okay, are in a different environment than this methyl group, right? Because these protons are all attached to a carbon that's attached to a carbon. Whereas here, this carbon's attached to an oxygen. So if I label this as environment A, this is going to be environment B. This is also environment B. This is also environment B. So we have just 2 types of proton environments here. Now, which proton environment do we expect to be the most shielded, producing the signal that's the farthest upfield? Well, the one that has the greatest electron density around its nucleus. So let's compare the electronic environments here. So these protons attached to a carbon, okay, that's attached to a carbon. These protons are attached to a carbon that's attached to an oxygen. Well, oxygen's very electronegative, so the oxygen-carbon bond is extremely polar, right? It's the oxygen is sucking electron density away. So we expect then these protons to have decreased electron density around them. So we expect them to be de-shielded, okay, relative to these protons. And you might say, well, the oxygen is attached to this carbon, which is attached here, and then you've got your hydrogens, but that's farther away. So this oxygen that's very electron withdrawing is farther away from these hydrogens than it is from these. So these protons, their signal should be the most downfield, the most de-shielded, okay? And that's in fact what we see. So they are making this signal here, and then these protons here are producing this signal here, okay? And because we have 3, 6, 9 of these, we have a more intense signal than we do here, okay? All right, so you should be familiar with these terms: upfield, downfield, shielded, de-shielded, and we'll practice more about predicting how to know which signal is the most upfield versus the most downfield. And we'll also need to practice more of determining the number of proton environments that we have in a given compound. Okay, so I think I'm on track now to talking about the last topic, which deals with the 4 important features in an NMR spectrum. And they are, number 1, the number of signals. You can also see this referred to as absorptions or resonances. So the number of signals tells us how many different types of proton environments there are in a molecule. Okay, so I'm going to make this about proton NMR. I'll put here a little proton, since that's the first one we're talking about. So the number of signals tells us the number of proton environments there are. The second important feature is the position of the signals. So this is the chemical shift. Okay, that little delta. So this tells us if the hydrogen is near a functional group. We can deduce that based on where the chemical shift is. Okay, And on your exams, you're going to be given a chemical shift table. This is an example of one here. This is showing characteristic proton chemical shifts, okay? And as we go through different families of compounds, we'll see their examples of those compounds and their proton NMRs, okay? And then later, we'll take a look at carbon NMR as well. But this table, you're going to be given on exam, so you're not meant to memorize this, okay? All right, let's move on. So the third important feature in a proton NMR spectrum is the area under the signal. I think your textbook calls this the intensity of the signal, okay? So this tells us the number of protons there are making up that signal, so in a given environment. And then the fourth important feature is the splitting. Okay, in your textbook, they call this the shape of the signal. Is it a singlet? Is it a doublet? Is it a triplet, a quartet, a quintet? This splitting is going to tell us how many protons there are on the carbon atom next door. So this is where we're going to use that n+1 rule. Okay. So what's going to happen now is in the next video, we're going to practice determining the number of signals or absorptions or resonances that we expect to see for a given compound in its proton NMR spectrum. And that takes some practice. And then we'll work on each of these in succession. As you're listening to these videos, keep in mind that we're going to focus on interpreting proton and carbon-13 NMR spectra. In this chapter, I will use examples from families of compounds that you saw in 301. So that includes alkanes, alkyl halides, alkenes, alcohols, ethers. And then as we progress in 302 and learn about different families of organic compounds, I will throw in then examples of proton NMRs for that family. So we'll talk about carboxylic acids later on, and amines and aldehydes and ketones and so on, okay? All right, stay tuned for the next video.